Okay, I'm switching it on. Okay, good afternoon, everyone. Good afternoon. Looks like thermodynamics has had quite a few casualties. Okay. All right, you ready for Monday? Okay, so here is a plan. I'm going to have a review session tomorrow afternoon. Whoever wants to come can come. It's going to be on Carmen Zoom. Okay, it will be recorded, so if you cannot make it, please feel free to see it over time. So review. Saturday, 2 p.m. to 3 p.m. Typically the review spills over, goes to maybe 3:15, 3:20 or so. I plan to walk through one of the problems and then I'll point out certain things that I feel one should maybe pay close attention to when it comes to the exam. Okay? All right, and then your exam, Monday, 11/7, I believe. The exam will open at 9 a.m. And the exam will close at 11:59 p.m. on Tuesday. And between these two time periods, you're going to select a 2-hour window. Make sure you're utilizing all of the time, if you can. Okay, within those 2 hours. So select a period of time where you are sure you're going to have 2 hours. Sit down, go over the exam very carefully. Okay, this is not going to be similar to exam 1. Exam 1 is a relatively simpler material. As you know, we've been doing it in class. Exam 2 is going to be slightly more challenging. It will be fair. It should be something that should be reasonably completed within an hour or a little more than an hour. But if I were you, I would take the full 2 hours. Okay? All right. And it's open book, open notes, but please follow the honor code. All right, any questions, please, before I proceed? Yes.
It's going to be like one or like 2 questions, like the first one.
I'm not very clear on that yet, but whatever it is, you also have to realize that I have to grade those papers, so I have to make sure that I don't ask too much, because I'm a lazy person. So 2 to 3 questions. I'm not lazy, I'm just saying it, but 2 to 3 questions typically is what I would expect. I would expect know your block diagrams really well. If I'm given a block diagram, how do I reconstruct the system model? If I'm given a system model, how do I do the block diagram? If you make a mistake in the block diagram, the question might ask you to do other things in addition to it. Okay, obtain the dynamic model, then obtain the step response. If you make a mistake in the block diagram, your step response is gone. So one mistake will have a domino effect. Make sure you're very careful when you're doing the block diagram analysis, okay? All right, any other questions, quick questions before I proceed? And I will have a lecture on Monday. I'm assuming the turnout will be low because I've been told you have another exam on Monday as well. I empathize with that. I've been in this situation. I've been a student for a very long time. I got my PhD here too. One thing that I have learned, everybody learns their lessons, individual lessons, but one thing I have learned is these difficult situations help you adapt to reality in a more feasible manner. Okay, so you learn to live with the difficulty, and you will see light at the end of the day. Sometimes you may not, but it is good to hope. All right. So we will have class on Monday. I will record it as such. I will make sure the content that is covered on Monday, a certain amount of that spills over onto Wednesday. We are going to go into difficult material. We are going to start off in a nice way because you might have seen this material before, but we're going to ramp it up after that. Okay? All right. So with that said, I'm going to start electrical systems, which you have seen in courses you've taken. My assumption is that a lot of you are in the circuits class. Some of you may have already taken this class. So I'm not going to spend too much time on the details of the different electrical elements because that is not my interest here. My intent is to quickly go over them to a certain amount of vigor and rigor, and then start designing systems that we can study using the techniques we have developed. Okay, Laplace transforms and so on. And so I'm going to motivate this by starting off with the definition of an electrical system. What's an electrical system? It's a collection of electrical elements which are arranged around a closed loop to transfer electrical energy or convert electrical energy or to dissipate energy. Okay, so this is the basic definition. It's a combination of electrical elements arranged around a closed loop which is a very important statement because this closed loop is called your circuit, the electric circuit, okay? And designed to dissipate or transfer electrical energy. And this closed loop is what we call as the circuit. In system dynamics, and as you would have seen in electrical systems as well, you are mostly concerned with two types of electrical elements: active elements, passive elements. Okay, and I hope these bring back some memories of the course that you are currently taking or perhaps have taken. So elements, active, passive. What is an active element? An active element is a source of electrical energy. So this is a source of electrical energy. Okay? Example, very simple, silly example is an alkaline battery. It's a source of electrical energy. It is capable of converting chemical energy into electrical energy. This is applied to perform some kind of an activity, right? Lighting up a bulb or lighting up the room. Okay, so example is a battery. And we will define in the next class an ideal voltage source, which is what we will be employing for all of our problems from now on. And I know that if you have taken circuits, you would have come across the Thevenin and the Norton equivalents and so on. We will not be employing such techniques here. Okay? Everything will be very nice and very clean. Passive elements, on the other hand, cannot convert energy from one form to the other, but they are capable of dissipating or storing energy. Okay, so these are elements that dissipate. Or store. The three passive elements that we will be looking at, and you know this really well: resistors, capacitors, inductors. Okay, so we're going to look at resistors, capacitors, inductors. Be careful. Capacitors and inductors, they are also capable of acting as sources of energy. But we are not going to use them in that particular form. Okay? We are going to use them as dischargers of energy. Okay? Essentially of that nature. So you could make use of them as a battery, or you could also use a battery as a passive element. If you have a rechargeable battery, then you need to charge that fellow. That becomes a passive element in that sense. Okay, so you can always have these conversions between the two, but for us the three passive elements will always remain passive, which means they cannot generate electrical energy, but they can dissipate or they can store electrical energy. Alright. And before going to other details, I want to define three things that we've come across in everyday life. Okay, three fundamental quantities of electrical systems. And these are charge, current, and obviously the next one is voltage. Okay? Simple stuff, very useful though. Current is a fundamental property of matter, whether you like it or not. You have some, charge, not current. Charge is a fundamental property of matter, whether you like it or not. You have some charge, positive and negative. It's a fundamental property of matter. And you know charge comes in two types, positive charge, negative charge. Okay, very elementary stuff. So positive charge, negative charge. An electron carries a negative charge. And the charge on an electron, this is something that one should remember, like a gravitational constant. A charge on an electron is given as minus 1.602, 10 to the power minus 9, C, capital C. Capital C is Coulomb. Okay, so unit of charge. This is the charge on an electron. Obviously the charge on a proton, which is the positive twin of the electron, is plus 1.602 10 to the power minus 9. Okay? Alright, unit of charge is Coulomb. Capital C. And in our course in system dynamics, we will designate charge as Q of T. Okay, so charge is a variable of interest for us, so, and it's a function of time as well. So we're going to designate it as Q of T. This is the designation. And as I said, I'm not going to dwell too much on these details. Okay? The second fundamental quantity is current. Current is charge in motion. or essentially the rate of change of charge is current. Okay, the current is charge in motion. And the symbol for current that we're going to use is I of t, little I of t. And this is instantaneous current, like you have instantaneous velocity, instantaneous acceleration, and so on. This is instantaneous current, not average current. Instantaneous current is the rate of change of charge. So this is dq by dt. These are the field variables that we are going to be using. Okay. Unit of current is ampere, named after Ampere. And this is named after Charles Coulomb. Fundamental experiments in electrostatics, electrodynamics. And I strongly suggest looking at the history of Charles Coulomb. He has also troubled you with friction. Okay, so the unit is ampere. Okay, or capital A. Amperes. 1 ampere, as you can see, is 1 coulomb by 1 second. Okay. So 1 ampere is 1 coulomb by 1 second, and so amperes is nothing but coulombs per second. Okay. One fundamental thing that we are going to employ, this is a convention that we typically use. Electrical systems have a lot of conventions. These are arbitrary in some sense. Some of them have physical routings as well, physical groundings as well. One convention that we're going to say is the direction of the flow of current in the direction of positive charge flow. Okay, which means the flow of electrons is opposite to the flow of currents in a circuit. Okay, the flow of electrons in a circuit is opposite the direction of current flow. And so far, no surprises. These are very basic things that you have come across in some form or the other, starting from electricity and magnetism courses in physics, and also your circuits course, hopefully. The last quantity is obviously voltage. Okay, the unit of voltage is volts, named after Alessandro Volt. Okay, but why do we need voltage? Right? Why do we define the quantity? I'm going to pull the top panel down, and in some sense, the best way to learn about electrical systems is by drawing an analogy with mechanical systems or drawing an analogy with hydraulic systems. Hydraulic systems is something that we're going to study after electrical systems. Okay, pull this down. All right, so voltage the last one. What's the motivation? Here is our aim. In electrical systems, our aim is to move charge from one point to another within a circuit. Why do we need to do this? Is because if I do that, then maybe if I have a circuit containing a battery and a bulb, I could move the charges from the battery all the way to the bulb lights up. Okay? So our aim is to move charge from one place to the other, and you would immediately think, okay, if I'm moving something from one place to the other, what do I need? I need some energy. So voltage is essentially the energy required to move charge from one point to the other. Okay? The voltage is the energy required to move charge from one point to the other within a circuit. Within a circuit. If I draw an analogy with mechanical systems, what could the analogy for voltage be? Yes?
Potential energy.
Potential energy, fantastic. I could also think of force, because energy is due to a force supply. So typically the driving variable in electric circuits is the voltage. Okay? If I have voltage, I have charge that can potentially move from one point to the other. And if charge is moving, what's going to happen? Current is going to flow through the circuit. Okay? Alright, and this is measured in volts. Capital V. And 1 volt is 1 joule per coulomb. What does this mean? This means if I have a battery rating of 1.5 volts, it means that I have 1.5 joules of energy to move a unit charge from one point to the other within a circuit. Okay? So 1.5 volts means that I have 1.5 joules to move unit charge. Okay, this is what you would call as a battery rating or something of that sort. Lastly, we define electrical power. Power. Some books use it as capital P, some books use it as small p. We will use little p. Power as units of watts. Right? What's a watt? A watt is 1 joule per second. I divide the top and the bottom by 1 coulomb. Right, capital C. And then I take the denominator, bring it to the numerator, this entire quantity. So 1 joule by 1 coulomb. Okay, this is 1 watt. Multiplied by 1 coulomb by 1 second. What does that tell you? Voltage is joules per coulomb. What is coulombs per second? It is nothing but current, which means that electrical power is voltage times the current. Okay? P of t. This is voltage, V of t, and this is I of t. Voltage is going to be represented by or designated as V of t for us. Just write this here. The symbol that we're going to use. Okay, so P of t is V of t, I. Once again, elementary stuff. Okay. Two things. One is, whenever you talk about voltage, you always refer to it with respect to a reference voltage. Okay, sometimes when you talk about pressure, you always talk about it with respect to atmospheric pressure. Right? You define a gauge pressure. So likewise, if you're talking about voltage, you always have a ground voltage that you act as a reference voltage. So voltage is referenced with respect to some standard value. Ground voltage is the standard. And for convenience, the voltage of a grounded point is considered to be 0 volts. Okay? So for convenience, ground voltage is 0 volts. Okay, so now I want to draw the analogy between electrical circuits and hydraulic systems or fluid systems, because we're going to study fluid systems next. The best way to remember all of these things is through the analogies. If you've read the document I posted, which says system dynamics in 10 pages or something, the last page is the only page you actually need to know system dynamics. That's the page which talks about all the analogies. If you know that page, you know system dynamics, move on with your life. Okay? So, I'm going to talk about a very brief analogy. This is a water tank. Okay, so here is a tank filled with water. Obviously, the top of the tank is open, so what's the pressure? It's going to be atmospheric pressure. Okay, so this is P suffix A. Atmospheric pressure. Let's say that the column of the fluid within the tank is of height h. And right now I have an outlet which I have stopped with a fluid stopper. Okay? But if I look at the pressure right at the outlet before the fluid hits the fluid stopper, the pressure here is it going to be higher or lower than the atmospheric pressure? It's going to be higher, right? If you know swimming, you know that you should go deeper and deeper. The pressure increases. You don't want to go beyond a certain depth. So this is atmospheric pressure plus rho times g times h. Rho is the density, g is acceleration due to gravity, height of the fluid. And what happens is that as soon as I remove the fluid stopper, what's going to happen? As soon as I remove the stopper, what's going to happen? Yes? Well, what's going to happen physically? The fluid will flow out. Okay? The fluid will flow out. And so you see, what makes the fluid flow out is the difference in the pressure. There is a higher pressure here, there is a lower pressure there, and that difference in the pressure is what makes fluid flow out. And so whenever we look at circuits, we think of the following analogy. The quantity of water in the tank is the quantity of charge. Okay? So mass of water. This is analogous to the charge in a circuit. The flow of the mass, as you know, mass flow rate, is now going to be our volumetric flow rate, whatever you want to call it as, is going to be analogous to the current flowing through a circuit. Right? If I remove the stopper, mass is going to flow at a certain flow rate. This is the same thing. I drive the charge by making use of some kind of a driver, then current flows in a circuit. Okay, so mass flow rate is analogous to current. And obviously, what is the driver in this problem? The driver in this problem is the pressure difference. And pressure difference is analogous to voltage difference across the terminals of an element. And this is an important thing. I am not interested in the voltage at a point. I am interested in the voltage difference across the terminals. Okay? So, the pressure difference is analogous to voltage difference. Voltage difference, or typically you also call it as potential difference, change in the voltages. And if you want to take it a step further, if you want to have an analogy with mechanical systems, what could be a good analogy for charge? If you think of mechanical systems. Yes? Mass. Fantastic. That's it. This is analogous to mass in mechanical systems. What's analogous to current in mechanical systems? Yes?
Velocity.
Velocity. Fantastic. And what's analogous to pressure difference or voltage difference is typically potential difference, potential energy difference, but we would think of the way that a mass moves is because of a driver, the external agent, which is the input force or the input torque. Okay? So this is analogous to all of these. Force or torque in mechanical systems. Okay. All right, now for some basic terminology in electrical circuits. Stuff that you've seen before, probably. We're going to define a branch of a circuit. What is a branch of a circuit? A branch of a circuit is nothing but an element and its terminals. Okay? So here is an element. Once again, this is common knowledge, I presume. And then we can have a circuit with different branches, and the points that connect these branches are called the nodes. Okay? So nodes, points that connect branches. Right, so I could have two elements, and wherever they are connected, here is a node, that's a node, this is a node, there is also a node. Alright, and slowly what we are going to do is, in about a few minutes, I'm going to go into the passive sign convention. The passive sign convention is the fundamental arbitrary way of designing how current flows in a circuit. And with that, we will now be able to talk about the current voltage relationships of the different elements. Okay? I'm going to pull the top panel down. And hopefully these are the same terminologies that have been used in your circuits class. Am I right? Or if not, I'm still right, so it does not matter. Okay, one more thing, then we are on our journey to passive sign convention. I'm going to take an arbitrary circuit. Okay? So this is once again going into nomenclature. The first thing is the ground is represented by the following. This is the representation of ground. So I could take any point on the circuit, say this is the ground point, okay, which means the voltage there is 0. So this is the ground. Let me consider one of the elements here. Okay, let's call this as terminal A. This is terminal B. There is going to be a certain velocity designated at terminal B. We're going to call that as VB. There is going to be a certain voltage, I'm sorry, not velocity, voltage denoted at terminal A as VA. Typically, you would have a plus and a minus sign accompanying that particular element. Okay? So this is what it means. Each and every voltage, VA and VB, are always written with respect to the ground, which means that the voltage VB is actually the voltage at that point subtracted from the ground voltage. The ground voltage is 0 anyways, so it does not make any much of a difference to us. Okay? So each voltage is referenced with respect to the ground. With respect to the ground. The second more important point, this negative sign here does not imply that the voltage VB is negative. Once again, I want to make this very clear. I'm sure you know about this. The voltage VB is not negative because of this negative sign. The negative and the positive sign tells you that the voltage VA is greater than the voltage VB. That's all it tells you. It does not tell you anything about the signs of these voltages. I could have VA being negative voltage, I could have VB also being negative voltage, one more than the other. Okay? So the plus and the minus signs indicate that VA is greater than VB, and so we are always interested only in the voltage difference or the potential difference, and so typically we will write the potential difference as VAB. So VAB is VA minus VB. This is the potential difference. Once again, this is just basic nomenclature. I have seen many people, even though people take circuits, you've done electricity and magnetism, I have seen people putting a negative sign to the voltage at B. It's not the meaning of that. It is just that the voltage at A is greater than the voltage at B. Okay? Alright, now we go to the passive sign convention. There is also an active sign convention. It's not followed as much as the passive sign convention, and these are completely arbitrary conventions, but the passive sign convention has a little more of a physical intuition. Okay? So I take what is called as a load element. And I take a source element. A load element is typically a passive element. For example, a light bulb is a load element because a light bulb takes energy from a battery. The coil or the filament inside the light bulb gets heated up, and energy is dissipated in the form of heat and light, and the light bulb glows. It's not a source of energy. What we do in electrical systems is we say, okay, instead of modeling it as a light bulb, I will model it as a combination of resistors, capacitors, and inductors. The exact same thing that we did for mechanical systems. I take the beam and I break it up into a mass spring and a damper unit. Okay? So a load element in some sense is nothing but a combination of passive elements. I want to make that statement here. Example is a bulb. It's a combination of passive elements. For example, if you have a light bulb, it has a filament, right? The filament gets heated up, which means there is energy dissipated in the form of heat. An electrical element that models dissipation is resistor. because of the fact that the filament is coiled and current flows through it, there is a certain self-inductance that is generated, which means that I can take a light bulb and model it as a series combination of a resistor and an inductor element, and I will get the same result. Okay, so that's what it means. So the passive sign convention is the following. When current flows through a load element, the current will always flow from a region of higher potential to a region of lower potential. So if I put the signs here, this is going to be plus, this is going to be minus. What does this tell you? It tells you that the charges are coming up with a large amount of energy because they're coming at a higher potential. In the process of lighting up the bulb, there is a lot of juice lost, and so they're coming out at a lower potential. Okay? So this is the passive sign convention. If I have a source element, according to the passive sign convention, the direction of current flow is from a region of lower potential, this is I of t, to a region of higher potential. And what does this mean? This means that if I have a battery, the battery takes in charges that come at a lower power, juice it up, give it a little more of a push, the charges come out having greater energy and they move out from the positive terminal. Okay? Does this make sense to everybody? Any questions on this convention here? Very standard. You've seen this before. This is all we're going to use. Okay? Now let me draw a hypothetical circuit. And you tell me what is going to be the direction of the current flow in the circuit. Okay? Okay, so this is a load, source, okay. What's the direction of current flow here? Is it clockwise or counterclockwise? Right, it has to be clockwise, right? Because current enters at the terminal containing the lower potential, leaves at the terminal containing the higher potential, goes all the way to the load where the load uses up all the good stuff. And so the direction of current is clockwise. Okay, so this is I of t. That's one example. Here is another example. Load, 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 source. Okay, so I have three load elements, probably overloading the circuit, but nevertheless, I have three load elements and I have one source connected together. Okay, I'm telling you that the direction of current flow is counterclockwise. What should be the signs? Let's start with this guy here. Okay, so this is the direction of current flow. When current enters a load element, it enters at a higher potential, right? A region of higher potential, and then it loses everything. So which means that it goes out at a lower potential. It's probably not lost all of its juice, so it enters the next load element and it says, okay, I'm entering a load element. So it is still at the higher potential terminal of that load element, loses all of its stuff, negative. Then enters the third load element. It's done a lot of running around. And then what about the source? The sign here is going to be negative and then positive. Okay. And why I am showing this is because in many circuit problems, I will just give you the circuit without specifying the direction of current flow. The signs may be put on it, or in certain circuits I might tell the direction of the current flow, but I may not put the signs on across the terminals of the elements. Okay, so one needs to know the passive convention to employ this particular idea. Silly stuff, but still very useful. And with that, I'm going to go into the three passive elements that we are going to study in this particular semester. Okay, so the VI characteristics or relations for the passive elements. All right, first one is a resistor. Okay, this is the British spelling. You can also have it with an E. It's okay, you can use either. So if I have a resistor is an element that is used to model dissipation in an electrical circuit. So models dissipation in circuits. What's its analogy with mechanical systems? It's a damping element. Okay, so this is analogous to a damping element. And the resistor is characterized by its resistance to the flow of current. Okay. Characterized by resistance to current flow through it. Resistance is a property, it's a material property, okay, similar to elastic modulus, similar to Poisson ratio. It's an elastic property of materials. Different materials have different resistances, all right, and the current voltage relationship is given by Ohm's law. We all know this from the time we were babies. Ohm's law says that the voltage drop across the resistor, notice the terminology, the voltage drop across the resistor, because the resistor is a load or a passive element, the current flows from a higher terminal to a lower terminal, so there is a voltage drop taking place. Okay, so the voltage drop, I'm going to label it here. This is the representation of a resistor. Capital R is the resistance of the resistor. Plus sign, minus sign, indicating that the flow of current is from right to left in this case. I of t. If I say voltage at the terminal plus is VA and voltage at the terminal minus is VB, then the voltage drop across the resistor is VR. And VR is essentially VA minus VB. So VR and Ohm's law says that this voltage drop is proportional to the current flowing through. The constant of proportionality is the resistance. I'm going to get rid of this figure here. Okay, I'm going to continue here. Now, I'm not going to live on the time domain. I'm going to go to the frequency domain, because our aim is to do frequency response in electrical systems. So what we're going to do is this. We're going to take that relationship I'm going to take the Laplace transform on both sides. Okay? So take the Laplace transform. Laplace transform. R is the resistance. This is measured in ohms, OHMS. The symbol being the Greek omega. R is a constant, it's a material property. Okay? So current is the one that changes as a function of time. And so if I look at the Laplace transforms, I'm going to have, instead of VR of t, I'm going to have capital VR of s now in the Laplace domain. This is equal to R times I of s. This is now in the Laplace domain. And as you know, s is sigma plus j omega, it's a complex number. And then we are going to define some quantity which you also know from circuits. It's the electrical impedance of the resistor. So ZR impedance of the resistor. Impedance in general, this is a transfer function. I have current flowing into the circuit, right, flowing into the element, and as a result there is some voltage drop taking place, or the cause and the effect can be mangled together, but essentially the impedance is defined as the Laplace transform of the voltage across the element to the current flowing through the element. Okay, so Z of S is the Laplace of the voltage drop across the element to the Laplace of the current flowing through. This is just the basic definition of the impedance. Okay? And so for us we have the impedance of the resistor as a ZR. Why do we do this? Why not stay in the time domain? Is because electrical signals are typically sinusoidal signals. They're harmonic signals. And when I have a harmonic input, I am not interested in the transient behavior of the system. I am interested in long-term behavior of the system or steady-state behavior of the system. So what we will do in about 2 classes down the line, where things are going to get really confusing, is we will say that S is no longer sigma plus j omega. We will get rid of the sigma. We will just say S is equal to j omega because the sigma captures the exponential decay, and who cares about it in steady state? I don't. We're going to look only at the long-term behavior, which is characterized by the carrier frequency omega. Okay? So ZR, and all of this will become clear in a couple of classes, is VR of S by I of S is equal to R. This is the impedance of the resistor element. We're going to derive 2 more impedances very quickly, not even derive, I'm just going to write them down later on next class.